Hey everybody, welcome to Golden Triangle University. My name is Randall Karcher, and it's a pleasure to represent Goliath Resources here. And I'll be presenting the results from our recent drill season at the Golddigger deposit, or the Golddigger exploration, and my research and how that plugs in on the genesis of the mineralization at the Golddigger property in British Columbia. And here's a forward-looking statement, because I'll be saying some things that are forward-looking. So, the Golddigger property is at the southern tip of the Golden Triangle of British Columbia. Here you've got all of the deposits that we're familiar with, some heavy hitters like KSM. And then down here is Goliath's land package. It has several properties. The one that we're going to be focusing on the most today is the Golddigger property, which has the sherbet. Yeah, and there's a big variety of different deposit types that you find in the Golden Triangle, epithermals, VMS, porphyries, and then just vein, breccia, stockworks, unidentified, unclassified kind of stuff. So Goliath's land package at Golddigger and sherbet encapsulates, Golddigger here, the jackpot over here, up here Treasure Island in the Cambria ice fields, and a large newly acquired section to the south, which has Blue Origin, which is an area we believe to be prospective for Rearg-style mineralization. It has increased over the last year by a whopping almost 30%, from 66,000 hectares to over 90,000. So we've been acquiring quite a bit of land, and this is land that's all close to the red line, which we heard a little bit about in an earlier presentation. It's the contact proposed by Kaiba that demarks the contact between the Stuhini group sediments and the Hazelton, or the Stuhini group sediments and volcanics and the Hazelton group sediments and volcanics. And it is considered to have a lot of the high quality, high grade prospects, properties, and developments in the Golden Triangle. And yeah, a lot of the newly acquired land also has the Cambria ice fields up here near Treasure Island and to the east, based off of new outcrop from receding ice. So the research that I've done and contributed to the to this project is done through the CASERM Research Consortium. The CASERM is a effort between the Colorado School of Mines and Virginia Tech, and it's aimed at connecting mining companies, producers, and exploration with graduate research to marry real-life application to these deposits to generate data that goes beyond what might be done over a drill season and actually provide value to these companies. So my role with Goliath is, as a graduate student, this is going to be covering a lot of my master's research, and the efforts to actually provide an actual impact to Goliath and actually give a deliverable that's worth something. So Golddigger right here is located 10 kilometers southwest of Dolly Varden and 25 kilometers northwest of Kitsault molybdenum. It's here on the western flank of the Stikine Island Arch, right here bordering on the Coast Plutonic Complex, including the Hyder Pluton and the Bulldog Creek Pluton. Mineralization here consists of several arrays of polymetallic quartz sulfide veins. Dominantly, the sulfides in there are pyrrhotite with lesser sphalerite, galena, chalcopyrite, arsenopyrite, and then variable gold grades commonly exceeding 5 and 10 grams per ton over several meters. And these veins are cutting the folded upper Hazelton volcanic and sedimentary rocks, as well as the overlying Bowser sediment rocks. It's cutting right through veins and through shears. And ever since its discovery in 2019, sherbet and the mineralization at Golddigger in general has been pretty contentious. There's been proposed models ranging from VMS to epithermal to orogenic even, and age ranges all the way from Triassic to Eocene and even later. So the actual system has been poorly understood, and that's where my research comes in to try to sort of delineate what's going on, because that's going to be important for exploration So the sherbet outcrop was the original discovery, as you can see right here. It is a vein that's cutting through these sediments, as I said. It's got local massive sulfide with disseminations throughout surrounding rock, where you've got on outcrop a highly silicified and altered halo around this actual sherbet outcrop. And you can see here a little bit closer how gossinous it is. And yeah, this is a dead giveaway for the surface. It's actually something that you can trace far over the mountain. So it's actually got a kilometer of strike, and you can follow it all the way a kilometer down dip. It's got quite the relief, 700 meters. And the actual confirmed area of sherbet alone is pretty huge at 1.8 square kilometers. It's something that we determined with over 90,000 meters of drilling from 2021 to 2024. We actually still have 105 drill holes just from this past season that are pending assay. And our geometallurgy has shown that we have really good gold recovery. So over 92% from a 30 or 327 micron crush. That's just being liberated from the ore at that crush. And almost 50% of that is free gold, not composite grains with anything else, but actually just liberated as just gold. So right here is a cross section that Goliath has of our sherbet and bonanza zones. These are our high-grade gold zones. Down here you have the volcanics from the Upper Hazelton. Overlying it, we've got Upper Hazelton sediments, and at the very top some Bowser. And we've got these granodiorite dikes that go through all of this. And then, yeah, of course, these red structures here. This is sherbet that I'm circling right now. As you see, it goes up through the sedimentary rocks. And then down here is bonanza, which generally follows the contact between the sedimentary rocks and the volcanics. And these are all structurally controlled by faults and shears. I'm going to be spending a lot of time talking about sherbet and bonanza, but we've got other ore zones as well, other prospective polymetallic veins and areas that we're targeting and exploring. So that includes the Goldzilla, Eldorado, Whopper, and Golden Gate, in addition to, as I said, sherbet and bonanza. I've got a couple of selected lithologies here to show you guys. This is some sherbet ore. Like I was saying earlier, dominantly pyrrhotite, lesser sphalerite, galena, chalco, rare arsino, and it occurs as these sulfides cutting through the quartz veins that are themselves cutting through these structures. And then bonanza, it's about the same right here. It's the same sulfide mineralogy, just going along that contact between the volcanics and the sedimentary rocks. And then we've got various miscellaneous veins that cover the zones I was talking about a moment ago, as well as just small sub 10 centimeter veins that go throughout the property in both the volcanics and the sedimentary rocks. And these are also auriferous. We find gold in these as well. We also have skarn that forms, particularly in the volcanic rocks. You can actually form skarn inside of calcium-bearing volcanic rocks, so in this case andesite. Right here we have garnet skarn, which is the more rare of the skarn that we see at Golddigger. It's more common to actually see pyroxene skarn, where it's dominantly pyroxene. And then lastly, we have those granodiorites that I was showing you in the cross section. And the granodiorite is interesting because you'll actually find veins that cut through it. These veins are, they have the same sulfide assemblage, though they're much rarer volumetrically. They're usually less than 1% sulfide. We'll also find native gold and bismuth tellurides in these granodiorite dikes, which is, it carries significant implications that we can get to a little later. So the research goals of my project here is to understand the process responsible for mineralization at Golddigger and to constrain the timing of mineralization. There are different deposit models and ages that are tossed around, but this has real impact for exploration, whether or not it's a VMS or an epithermal or an aerogenic or a porphyry. I mean, these have significant implications towards exploration, and if you misinterpret the model, you might target based off of something that's just bunk. So we want to actually constrain this model and also the timing, because the timing of mineralization is going to have implications for where to look, because there are certain lithologies and structures that can't be exploited if, of course, mineralization comes in before those structures do. So the methods used include just normal petrography, so reflected and transmitted light microscopy on both thin and thick sections, a fluid inclusion study, which I'll explain in a little bit, optical cathodoluminescence imaging, I'm just going to say CL, automated mineralogy, I'll also explain that one, scanning electron microscopy with energy dispersive spectroscopy, I'm not saying that again though, so SEM-EDS, and then we used electron microprobe analysis on the actual precious metal phases. And then we did a lot of geochronology to really nail down the system. We used rhenium, osmium, and uranium lead. So I'm going to start with the fluid inclusions, and I'm going to give an overview of fluid inclusions just to get everyone up to speed. So veins are formed through hydrothermal processes, be it magmatic hydrothermal, or you can invoke metamorphic fluids or even meteoric fluids. These veins, most veins, form through hydrothermal processes. And these fluids actually can get trapped inside of the vein as it forms through various processes inside of different minerals. We used a lot of quartz. And the actual conditions of those inclusions will tell us the conditions that formed the veins. So you can actually, if you carefully select and measure them, tell pressures and temperatures for entrapment, which is obviously going to be something that's important because different deposit types have wildly different temperature ranges for mineralization and pressures. Another thing is post-entrapment modification of fluid inclusion. So not only do these fluid inclusions get stuck inside of various minerals, but they can actually become modified by significant pressure fluctuations. So fluid inclusions that are trapped and then exposed to much greater pressures kind of buckle in and modify that way, whereas a fluid inclusion that's entrapped under very, very, very high pressures and then brought to much lower pressures can explode. And we can interpret these textures to discern, okay, these inclusions have been modified due to incredible pressure fluctuations. And one way that's very well established to cause these fluctuations is actually crossing the brittle ductile transition. So you go from ductile conditions to brittle conditions, and the pressure difference there is way greater because all of a sudden you're going from lithostatic pressures to hydrostatic pressures. So the fluids experience much greater pressures lithostatic than hydrostatic because once you get into the brittle realm, you're connected to a fracture network, and that depressurizes the fluid by a very great amount. So by forming a fluid inclusion in the ductile regime and bringing it up to the brittle, you'll get modification. And if you hover around the transition, you'll get both types of modification. And that's exactly what we see at Golddigger. We see two distinct generations of quartz. The first we call Q1, and it's followed by Q2. So in the case of Q1, it's usually pretty opaque and dirty looking, and that's because it has abundant post-entrapment modified fluid inclusions. It's really pock-marked and just really beat up, and it's very anhedral for the most part, and it's really recrystallized. And then we have Q2, which is found overgrowing Q1. It's usually euhedral to subhedral as those overgrowths, and its fluid inclusions are not modified in the same way. In fact, no fluid inclusions in Q2 have been observed to be post-entrapment modified, whereas in Q1, many of them are, and there are some late secondary fluid inclusions that cut through and are not modified. But the point we're making here is that there are two distinct phases that have experienced different fluctuations in pressure. Specifically, once you have Q2, you're not getting those same fluctuations in pressure. And we see that the sulfides post-date Q2. So we can tell that through cross-cutting relationships, and we'll carry on, and I'll show you more of that in a minute. So in these generations of quartz, you can see here that the sulfides actually cut right on through both Q1 and Q2. You can see it's going along grain boundaries here. And yeah, these generations of quartz are in this sulfide matrix. By using CL, we can actually measure the difference in response between these two phases. So in the case of Q1, it has this sort of mottled, heterogeneous grubby looking response, but Q2, as opposed to Q1, you can actually see it's much cleaner, and you can actually see growth zoning inside of these crystals, which is a very different response than Q2. So you see the growth zones in this Q2, which is different from Q1, and you see that those growth zones actually have primary fluid inclusions that occur along the growth zones. That's pretty significant because by measuring these fluid inclusions, we're able to tell where this quartz was in pressure, temperature, space as it grew. It also has arsenopyrite inclusions along this growth zone. So by using microthermometry, we're able to determine the temperature that these inclusions homogenize at. And we get a temperature of 350 degrees. And since we know these were entrapped as a single phase fluid, we know that mineralization had to have occurred at over 350 degrees, which is pretty hot. We're also able to determine that the CO2 content in these fluid inclusions is really high. Actually, over 7 to 10% of the inclusion is CO2, both vapor CO2 and liquid CO2. And given that they homogenize at 350 degrees, we're able to determine that that has to occur at a hydrostatic pressure of about 500 to 600 bar at least. And since that's hydrostatic, we know that that means it's 5 to 6 kilometers deep. So right off the back, we know that this can't be a VMS or an epithermal because it's 6 kilometers deep and wicked hot. So that alone is telling us a lot about the system. So now we get into the petrography. The reflected light shows that Sherbet and Bonanza have effectively the same mineralogy that's determined macroscopically, so mostly pyrrhotite, sphalerite, galena. There is a difference in the trace minerals. So in the actual sedimentary hosted stuff, we find a lot more sulfur salts and more silver-rich minerals like tetrahedrite, stephanite, and pyrargyrite. Whereas in the volcanically hosted mineralization, we're getting bismuth-gold correlation. And we have a hard time actually telling a paragenesis from the sulfides because everything has weak annealing textures and static recrystallization. So that destroys the primary textures, and you can't really determine cross-cutting relationships the same way. One example of a sulfide that you can determine the cross-cutting relationships, however, is acanthite. So as you can see right here, the acanthite cuts right through the pyrrhotite and the quartz. So we can be sure that that comes in late. Next, we did automated mineralogy. I'll give you a quick crash course on that. Effectively, we use the equipment at the Colorado School of Mines to take a given sample and analyze a grid using EDS along the sample, and then we reference that to our internal database, and we're able to determine a mineral identification for each one of the grains. And by plotting that onto an image of the sample, you get a false color image showing all the different phases. And that's really helpful for showing paragenesis and alteration. For example, we have here just a billet from a thin section, and it's a gray rock. I mean, you can see that these are hornfells, and I tell you this is a mudstone. You probably see this sulfide halo, which is pyrrhotite, or a sulfide vein with a halo. But it's hard to say much meaningful just at a glance. But once we take this into automated mineralogy, all of a sudden the phases become obvious and you can actually tell a pretty distinct paragenesis. So you can see that these hornfells include andalucites and chloritoids here. The pink is the andalucites, the chlorite chloritoids are the light green. And you can see that this pyrrhotite is associated with quartz in that sort of tan color, and the red is biotite. And we've got anorthite associated as well, which you see that it's cutting right through this metamorphic aureole. So let's do that with the next rock. This is an andesite-hosted gold-bearing quartz sulfide vein. You could probably see the andesite. You might guess that there's some sort of alteration going on. Quartz and sulfide, yeah, sure, but we take it into automated mineralogy, and now you can actually see a case bar halo around this vein, very strong right here. So you can see that that's a high temperature halo around this quartz vein. And inside the vein, you can discern that there's pyrrhotite, which is this sort of brassy color, and then it's harder to see, but there's sphalerite in there, which is this brown. And it's associated with the green, which is actinolite, which matches our macroscopic observations at Golddigger as well, that a common alteration mineral we see associated with sulfides is actually actinolite. So one more vein, this is a quartz sulfide vein in some mudstone. In automated mineralogy, you can actually see that there's this biotite halo around the quartz vein, and the same actinolite pyrrhotite association that we saw in the last sample. So you're starting to get an idea, okay, we've got these veins, we've got biotite K-spar alteration. Well, it's harder to see in the presentation here, but there's a very small lime green assemblage, which is cutting through both the biotite and the actinolite here, and that's chlorite. But I don't expect you to take my word for it. So we take this into the SEM EDS, and we are actually able to get better images of this chlorite. And it turns out it's the youngest alteration assemblage. We can see here this chlorite is actually eating away, fanning into the biotite and going along cleavage and actually replacing biotite with chlorite. And another thing is the chlorite is commonly associated with gold mineralization. So right here we have veins of chlorite going through and actually replacing actinolite, and the gold is occurring with the chlorite. It's occurring in these veins and along these veins. The chlorite, the latest stage alteration, is also found to be associated with bismuth minerals and intergrown with molybdenite. So in this case here, it's very pale, but there is chlorite that runs through and along this pyrrhotite quartz boundary and up through here. And you can see that it's associated with what's labeled here as gold and native bismuth. And in the center here is actually an intergrowth between gold and bismuth, all associated with the chlorite here. In the case of the molybdenite, it's even more clear-cut because you have the chlorite going around, but also in between sheets of molybdenite. So you have sheets of chlorite growing with sheets of molybdenite. So yeah, that's a well-established relationship. Now that's important because what I've just established here is that we have a high temperature to low temperature gradient in the actual alteration assemblage, which I'm going to touch on a little bit later. Next, we take those precious metal grains that I just showed you and bring it to a microprobe. And we are able to determine the chemistry of the native gold, native silver. And what we find is that the location of where the sample was taken is very important, and it clusters distinctly depending on where it was taken. So here I have orange, red, green, yellow for electrum, and then this blue here is native silver. And you can see not only are they clustering by their position on this ternary diagram, but as you enrich in antimony, you enrich in silver, and vice versa. So there's a correlation between antimony and silver that we find in the actual precious metal grains. And that's something that you see by correlation matrix as well. The silver is strongly associated with not just antimony, but also arsenic and mercury. So that's really important because these are mobile elements. These are elements that concentrate away from a heat source or a fluid source. So the fact, and same with silver in fact, so we're seeing a concentration in mobile elements away from something. Well, if I bring it to the cross-section again and I actually plot these data points, it gets you a better idea of any potential zoning that could be going on here. Both of our high gold precious metal grains are found in the volcanics, ranging from about 80 to about 70 weight percent gold, the rest silver, and there's a very low amount of antimony, not an appreciable amount. As we get up into the sedimentary rocks a little bit, that sample is a little bit more than 50% gold and a little bit less than 50% silver by weight. So definitely a lot more silver enriched than what we're seeing in the volcanics. And we're also starting to detect an appreciable amount of antimony, 0.2 weight percent. And that changes when you go all the way up the structure, where these grains that we analyzed is just loaded in antimony. It's 3.3% antimony. It's only 30% gold by weight and 66.5% silver. So you're definitely getting this concentration along with antimony up the structure. Last, we wanted to have a meticulous geochronology set to really firmly place in time where Golddigger is. So we started with the garnets. We uranium lead dated the garnets here. As you can see, the sulfides cut right on through the garnet. So the idea here is it gives us an oldest possible age for mineralization at Golddigger. And so using laser ablation, we're able to actually measure the uranium lead values in here, and we get an age of 54 plus or minus 1.6 million years. So that's Eocene, a strong Eocene signal. But like I said, we wanted to be meticulous. So we've also dated those dikes, which we know host gold bismuth mineralization. We get zircons out of these dikes, we do laser ablation on them, and we get 52 million years plus or minus 1.5. That's another very strong Eocene signal. Lastly, we do rhenium osmium geochronology. We do that on molybdenite at Erie in Fort Collins, Colorado. And we are able to analyze this molybdenite bearing vein right here. And we get 50.7 plus or minus 1 million years. So that's 3 different geochronological methods that all say Golddigger is Eocene. So what's the big deal about that? Well, there's strong evidence that Golddigger is what you'd say is an intrusion-related system. So that first starts with the fluid inclusion evidence, which says it's a very deep, very hot system. So that's already going to throw out something like a VMS or an epithermal. The high CO2, we call them double bubble inclusions, is typical of a intrusion-related system or an orogenic system. So why isn't it orogenic? Well, tons of reasons. First being that there is strong evidence for a mineralogical gradient, not only in the actual alteration assemblage where we see high temperature pro-grade alteration minerals like garnets, pyroxene, K-spar being overprinted by much cooler, lower temperature alteration minerals like chlorite, but we're also seeing a concentration in mobile elements correlating to silver inside of the actual precious metal grains, which is not common at a deposit scale in an orogenic system where you would expect typically to have chemical values in the precious metals to remain relatively consistent over a kilometer distance, as opposed to what we have at Golddigger, which is a radical difference over a geologically very short distance. We also have a coincident age with the Alice Arm intrusive suite. That's the intrusive suite responsible for the Kitsault molybdenum porphyry, which is about 55 million years. So this isn't the first example of Eocene mineralization nearby in the Golden Triangle. Real nail in the coffin is the intrusion-hosted gold mineralization that we find in those dikes. That would be remarkably atypical of, say, an orogenic deposit, but that's textbook for something like a reduced intrusion-related deposit, where you get a strong gold bismuth association in a reduced felsic intrusion at depths of greater than 6 kilometers at temperature ranges that we found in our fluid inclusions. So what are the implications? Well, this is the first solidly confirmed Eocene intrusion-related gold mineralization in the Golden Triangle. And it's suggesting that Jurassic features and younger features like the Skeena Fold and Thrust Belt and the Coast Plutonic complex might actually be overlooked. We might not be looking for Eocene gold mineralization the same way we're looking for Triassic-Jurassic gold mineralization, since it's not nearly as well established. So we might be overlooking that in our exploration. The classification also has implications at Golddigger itself, since intrusion-related systems have distinct geochemical vectors and mineralogical vectors that you could go to find a causative intrusion, which are well known to potentially host gold mineralization as well. So, yeah, the point of all this is to show that bringing this sort of research into the realm of exploration geology can actually have benefit and actually give you insights to the system. That's all she wrote.